sometime in 1995 or 96. Actually, it was invented in 1960s though, okay, by VC, Vapnik and Chebronenkis, who has developed several machine learning theory. Now, since they are in Russia, nobody knew about it. Now, once Russia somehow split and all those, you know that in 1990s, there were some issues in Russia and they've split into several countries. And Vapnik traveled to USA and joined IBM lab, I guess, or Bell lab. And then he was working with them. And one day he went out to have coffee with some of the big scientists of that institute organization. And then they are discussing on some problem. In the meantime, uh, that person said Vapnik that then about the about one problem, and Vapnik says that why don't you apply a method on an algorithm that we have developed sometime in 1960s. Then he explained what SVM is, support vector machine is. Then that person got surprised. Such a nice and powerful classifier. Why didn't you tell us earlier? He said, no, actually, because of all issues, we didn't publish it. And immediately after that, they published a paper. Okay. And within 6 months, SVM became the number one classifier. Okay. So support vector machine is very, very powerful, and underlying mathematics is fantastic. Okay, it is based on simple concept of class 11 maths, I'll tell you. And obviously there is that the basic concept is class 11, okay, straight line equations, and there are some vector operations. We have to understand the vector dot product, all which all of us know about it. And obviously there is some optimization technique, operation research optimization technique, quadratic programming problem. Okay, so that is only thing, maybe a bit higher mathematics, but whoever has studied operation research, they must be knowing quadratic programming problem and how to solve it. Okay, however, I'll try to explain, though obviously we will not discuss the operation research or how to solve and how to prove what is the solution and all those things. We'll assume something, and I'll try to explain SVM from the machine learning perspective. I'll start with a presentation which I got from Professor Pavitra Mitro of IIT Kharagpur, and then I'll explain the basics of SVM that would help you to understand, okay, from my notes. Frankly speaking, when I learned SVM, okay, I read it, it was a bit difficult to understand. Then actually though obviously in a paper, right, everything is not written from the scratch. They will assume you that you have got certain knowledge and you are familiar with everything, and they have explained. And then in fact I thought about it, and I took almost 15 days at how to explain SVM to a undergraduate student, okay, so that everybody understand and don't get bored, and they will be able to appreciate the underlying mathematics, okay, the concept the Vapnik and Chebronenkis has in or used in developing this SVM. Okay, so this is one of my favorite topic, as I said, in machine learning. So I'll try to explain, and please ask me questions if you have any doubt. I am telling you, if you listen or if you try to learn yourself, it will take long time. But if someone explains you who has understood up to a certain extent, I'm not telling that maybe I understood very or everything, but I'll try to explain whatever I understood. Then if you have any doubt, please ask me. Okay. So I'll start with the presentation of Povitro, and then we will go ahead with the minus. So this is let me explain you the problem. First, as earlier classifiers, whatever we discussed, we will start with simple linearly separable two class problem. Okay. Suppose we have two sets of data. One is red, another set is blue marked here, and it is a binary classification problem. Okay. And it is linearly separable. The primary objective to classify this type of data, what we want a line, straight line, right, linearly separable. And from the beginning itself, we are trying to find out how to find a boundary that would separate two classes. That is perceptron, right? Perceptron learning algorithm we have learned. And here this line is represented as, we are familiar with this, right? W transpose X plus B equal to 0. As I said, in the PLA or in neural network, we have considered the dummy variable in X, but here we didn't introduce that. We have excluded the dummy variable. X d-dimensional means this X vector has got X1, X2 up to XD. So W is also a d-dimensional weight vector or parameters. It's like, see, if you have an equation like AX plus BY plus C equal to 0, what it is written as W1 X1 plus W2 X2 plus B equal to 0. The bias term or the constant term is B, and W are the coefficients of the axis. W transpose X plus B equal to 0. And we know, right? You take a point like this one, then you put in this equation in the left hand side. If it is less than 0, we say that that is in the right side. If it is less than 0, we can say that is in the greater than 0, then it is in the left hand side, or vice versa. Does not matter. One side will be greater than 0, another side will be less than 0. That is the normal classification, and this is how we represent it, right? That fx, the level of the new of an unknown point, will be equal to sine CIGN, W transpose X plus B. This is, we are very much familiar. Now, question is how to find this line. We have learned a technique in PLA. We have learned some technique in artificial neural network, right? How to do that one in the classifier. Now here, let us consider that how many different lines there can be, okay, that can work as a separator between two classes. As you see, that there can be infinite number of lines one can draw in between these, isn't it? So, which of these lines will you take? Will you be happy to use as a boundary, okay, a separator? This line, second line, or maybe this one. If you take this one, maybe if you have a point somewhere here, right, you would like, if this point will be classified as blue, but we would prefer to classify this point like somewhere here as a red. Now maybe sometime which is equidistant from these two classes, right, will be a better one. Let's see some more. Now there are some boundaries, okay, line I am showing. Is it a good line? Because this is inclined towards this circle, right, this side. Now if you have point here, we would prefer to classify that point in the circle, but this point will be classified as a rectangular side, isn't it, class? So many decision boundaries are available, possible. The perceptron algorithm can be used to find such a boundary. Perceptron provides one of the infinite lines in between that it does. Are all decision boundaries equally good? That is the question. Now, there are some examples of bad boundaries. This is a boundary, we do not like it. You would have like to put it something in between these two. Here it would have been shifted, right, upwards. This side maybe would have been good. This one, it is inclined this way. Maybe you do not want that, but you rotate and make it something like this, right? Would have been better. So this is not a very good boundary. This is also not a very good boundary. This is obviously separating that this whatever given data you have, but that does not mean that it will work for out of sample data as well. This one also same thing. Here, the point you would like to put in that rectangle, but it would be classified as circle. This side, right? The same way. So these are examples of bad boundaries. Now you see. Better linear separation. You see, if you have a line something like that, now this here, distance from this set of points, rectangular set of points, right, from this boundary is small. Now here and all those things, here, what we want, the separation between the two classes should be higher. If the separation is higher between two classes, if you draw a boundary, that would, for that, the separation between two classes will be higher. Now, if you have a boundary like this, then the boundary or separation, right, width of the separator, this is called width of the separator, and we will refer that as the margin is very small. Now, see in this case, this boundary is in between these two, inclination is proper, and the separation margin is quite high. So compared to these two, we will prefer to consider this one as our separator. And frankly speaking, SVM tries to find out this particular separator. Now there can be, as I said again and again, there can be infinite number of lines you can find out, but our objective is to find a line that would separate two classes of data, two sets of data. That is the first objective, right, in the classification. And second one, we are just adding here the separation margin or separation width should be maximum. Okay, so first is that classify the points, given points correctly. That is the first objective in any classifier. And second one would be to find a line that would give us the maximum margin. Two objectives. Okay. Now, here, this is one example. You can see here, that means two sets of data you can do here. We'll prefer to have somewhere here, right, in between. This is also not very good. This is maybe a better one, or maybe it would have been better like this. This one is not so good. So somehow this is towards the circle. This is maybe a better, but inclination is not proper. This one is again somehow biased in the plus side. This one is biased in the other side, right? Now, you see here, dichotomies with big margin. These are the big margin, right? These 3 points in one class, this side is another class. You just draw, instead of drawing somewhere here, you just draw here. You see, this one provides maximum margin. This one also gives. So this is, big margins imply fewer dichotomies. Okay, that is a very nice one. As I was trying to explain it through BC dimension, maybe later you can listen to Abu Mustafa's lecture, generalization, then you will be able to appreciate this in a better way. So where the line should be, given the examples, you see the separators, right? These separators, whatever in different cases we have, these are the best. There are different lines you can draw for anything, any instant you can take, but the line drawn here are the best. Okay, now one thing, try to understand, and then I'll go back to my note. What the problem is, you are given, say, x1, x2, maybe capital X and X capital N number of data set you have, and each data point has got one label, and labels are here +1 or -1. So there are these points for which the labels are -1, and for these points labels are +1. So that we can, if I draw a line somewhere like this, which is W transpose X plus B equal to 0, so what we can write here, Fx or Y label will be equal to sine of W transpose X plus B. You know that, right? If you have a line here, W transpose X plus B equal to 0, then for all these points, W transpose X plus B will be greater than 0. For all these points, W transpose X plus B will be, sorry, this one less than 0, this will be greater than 0. We know that. That is a class 11 coordinate geometry, whatever we studied. So one line split or partition a plane into two parts. One side is greater than equal to 0, another side is less than 0. Okay. Now, what we want, this is fine. Not only this. Now, can I find a line which is parallel to our separator, just attached to the boundary of this circle class, here as well as here? And what we want, this line should be in between these two, right? So this distance and this distance are same. Now, this line is W transpose X plus B equal to 0. Then we can always represent by adjusting W and B, this constant, these lines as W transpose X plus B equal to 1, and this line as W transpose X plus B equal to minus 1. And what this W is, we know in the from the coordinate geometry, analytical geometry, W is called the direction ratios, right? We know that direction ratios, and this is a vector which is perpendicular to this line. If you draw a line perpendicular on this boundary, right? So this direction W defines a vector in the direction of the normal of this line. So how can we explain, how can we represent this boundary of this circle class and boundary of this rectangular class as W transpose X plus B equal to 1 and W transpose X plus B equal to minus 1? I'll explain. I'll stop this one and explain from my presentation, my notes. Okay. I'll stop sharing this and then I'll go to my note and I'll show you. Which one? SVM notes. Okay. Now I hope you can see this, right? Hello?
Yes, sir.
Okay. Actually, I was teaching in our college in MTech or BTech, I think, machine learning course. There I taught on 3rd of April 2020. That's why this note I prepared. Otherwise, normally I write on board. Anyway, again, I'll just repeating that here the same thing. We have got this data. Xn is a vector, d-dimensional vector. Yn are the levels. That is, Xn belongs to Rd, d-dimensional real space, and Yn are at +1, -1. Now see, we have two classes here, right? Suppose plus, and there are several other points around this. There are several other negative points around this one, levels -1. Here, these points are level +1. Now you see, this is the boundary of the plus class, this is the boundary of the negative class, and our objective is to find this one, which I have written W transpose X plus B equal to 0 by adjusted W such that boundary of plus class becomes W transpose X plus B equal to +1, and this becomes W transpose X plus B equal to -1. Now, I'll try to explain how it is possible. Now, here, again, just come to the objectives of SVM. As I said again, the points to be classified correctly. All the points in this class, right, that should be W transpose X plus B should be less than 0. For this class, W transpose X plus B should be greater than 0. So, first objective is to classify the given points correctly. Another one is to separation width between two classes to be maximized. There are several avenues, frankly speaking, one can draw between two classes, but we are looking for the avenue that provides us, right, maximum width, isn't it, or maximum margin in SVM term. Okay, so what we can write, if you have a point Xn in the plus class, W transpose Xn plus B should be greater than 1. Assume that it is 1 is possible. I'll explain that. It should be greater than 1 when Yn is +1. Level is +1, then it should be satisfied. If it is -1, then W transpose Xn plus B should be less than -1. Okay. Now, combining these two, this Yn is the level, can we represent these two sets of equation in one? If you have, say, capital N number of data points for all n. These are given, right? Can we combine or generalize these two? That we have done in logistic regression once. I will explain that once again here. Now you multiply, when yn equal to plus 1, multiply y1, yn, multiply both sides by yn. You multiply this side with yn is plus 1, so yn into w transpose xn plus b, right? That's what I have written. Since yn is plus 1, so this side remains as 1, correct? So it is greater than 1. Now for the second one, when yn is minus 1, if I multiply left side w transpose xn plus b by yn, this expression will come, and this minus 1 will become plus 1. And whenever you multiply an inequality by a negative number, the inequality changes, right? It will become greater than, that we know. Minus 2 is greater than minus 3. Now if I multiply by minus 1, 2 is less than 3, right? That is the normal thing we have learned maybe in class 1, 2, 3, 4, or maybe 5, 6, inequality. So combining these two into one expression, I feel it is again a very good mathematical use, of mathematics, isn't it? Instead of writing this one for yn equal to plus 1, this one for yn equal to minus 1, what we can write in one short, right? Yn into w transpose xn plus b is greater than 1 for all n, right? Does not matter whether it is in the negative class or in the positive class. This is the generalization. Okay, no issue. Now come to the w. I'll come back to this, but let me explain first how can I adjust w so that this becomes w transpose x plus b equal to plus 1, w transpose x plus b equal to minus 1. And to explain this, I'll take you back in maybe class 11 or maybe before that. Now let me explain that in simple 2 dimension, and always we can extend that to higher dimension case. Tell me, what is the equation of a line, normal form of a straight line? If you have a line somewhere here for which the perpendicular distance from the origin is p, and this normal, right? This is called normal, that makes an angle alpha with x-axis, right? The equation of this line is x cos alpha plus y sin alpha equal to p. We are very much familiar with that. Suppose you are given an equation ax plus by plus c equal to 0. We have converted the line into normal form by dividing both sides, right, or coefficients by root over a square plus b square. We know that. So that coefficient of x can be represented as cos alpha, and coefficient of sin y will be represented at sin alpha. Why it is sin alpha? Actually cos of 90 minus alpha. If this angle is alpha, the other one is 90 minus alpha. And in 3 dimension, what we do? In 3 dimension, whenever we found a plane, now if that plane, then you draw the normal from the origin to the plane, perpendicular. If that perpendicular makes an alpha with x-axis, beta with y-axis, and gamma with z-axis, then cos alpha, cos beta, cos gamma are called the direction cosines, right? And the equation of the line, if the perpendicular distance of the plane from the origin is p, we can write down x cos alpha plus y sin alpha plus z cos gamma equal to p. That is the normal form of a plane, isn't it? In 3 dimension. In 2 dimension, it is sin alpha because this beta here is 90 minus alpha. So this is the normal equation, isn't it? Okay. Now, what is cos alpha, cos beta, or cos alpha, cos beta, cos gamma in 3 dimension? That we referred as direction cosines, right? Cos alpha, cos beta, cos gamma, direction cosines. Now, sorry. Now, what we can do, in general, we have seen that now you can multiply this x cos alpha plus y sin alpha equal to p by any constant, right? Then equation becomes ax plus by plus c equal to 0. That ab, right? Or in 3 dimension, normally plain equation of right, in normal form we write as Lx plus My plus Nz equal to P, right? Where Lmn is direction cosines. But we can always write the equation in the form Ax plus By plus Cz equal to P, equal to say another constant, right? Maybe R or C or something. Ax plus By plus Cz equal to maybe D. Now, what those ABCs are? ABCs are direction ratios, right? Actually, Lmn, ABC, they are the vector towards along this normal, right? Lmn is the unit vector in this direction, whereas ABC are a vector, maybe it is not unit length, right? It is not a unit vector, but it is a vector in the direction of the normal. Now, how to convert that to unit vector? You divide that by its magnitude, root over a square plus b square plus c square. Correct? So that is the direction cosines, direction ratios we are familiar with, and we know cos alpha, cos beta, cos gamma, right? That is the unit vector along the normal, isn't it? And here, cos alpha sin alpha is the unit vector in this direction. And Ax plus By plus C, same line is represented as Ax plus By plus C equal to 0. Then we know A by root over A square plus B square, B by root over A square plus B square is the unit vector in this direction. And other way, and AB is a vector in this direction, right? And magnitude is root over A square plus B square. We know that. So it is clear now, I guess. Okay. So now here, if I have an equation x cos alpha plus y sin alpha equal to P, now what are these two lines? These two lines, this line is the boundary of the plus class, this line is the boundary of the negative class. And where did we draw this line? This line is in between these two. So if the distance, if this one is R, this is also R, right? Equal distance. So this total width of this avenue is 2R, correct? Now from this point to this line, right? Our line x cos alpha is P. Now if this distance is R, what would be the equation of boundary of the positive class? It should be same, because vector, unit vector in this direction is cos alpha sin alpha. So it is x cos alpha plus y sin alpha. And what is the perpendicular distance? That is P plus R. And what is the equation of this line? It would be x cos alpha plus y sin alpha equal to P minus R, because distance from origin to this line is P minus R, because this is P and this is R. This is R, right? So P minus R. So it is accepted, right? Now, if this equation is x cos alpha plus y sin alpha equal to P, and this line, which is R distance from this line, the equation has to be x cos alpha plus y sin alpha equal to P plus R, and this line will be x cos alpha plus y sin alpha equal to P minus R. Now, cos alpha sin alpha are the direction cosines of all these three lines, right? They are parallel. Distance from the origin of our line is P, distance from the origin to the line of the boundary of the positive class is P plus R, and negative class is P minus R. Okay? Now, come to this one, this equation. Now, this is a simple mathematics I'll do. Suppose this is the line, right? Now, take this P in the left hand side. Our objective is to write this one as W transpose X plus B equal to plus 1. This one is W transpose X plus B equal to minus 1, right? Let's see how we can write it. To take this P in the left hand side, I can write it. Now divide both sides by R. Okay, so this one becomes cos alpha by R into X, sin alpha by R into Y. This is minus P by R, right side is 1. Actually, objective here is to make the right side 1. Okay, that's what we had, isn't it? We wanted 2. Here, oh, so many mosquitoes around. So here, this cos alpha by R, this is a constant, right? And this is sin alpha by R. As I said, then cos alpha sin alpha was direction cosines. You multiply them by some constant, it becomes direction ratio. So I can always write cos alpha by R equal to W1, and sin alpha by R is equal as W2. So what we can write here? W1x plus W2y and refer this minus P by R equal to B, which is equal to 1. This and these three are constant, right? So I can write in 2 dimension as this. In 3 dimension, it would be W1x1 plus W2x2 plus W3x3, or W1x plus W2y plus W3z plus B equal to 1. And that can be written as, in general, in higher dimension, you can go, and it is W transpose X plus B equal to 1. So if this equation, I can write W transpose X plus B equal to 1, and we know what this W is. W1 is equal to cos alpha by R, sin W2 equal to sin alpha by R, and W and B is equal to minus P by R. Now come to the line in the negative boundary. X cos alpha plus Y sin alpha equal to P minus R. You take this P in the left hand side, divide both sides by R, X cos alpha by R plus Y sin alpha by R minus P by R, which is equal to minus 1, right? Then cos alpha by R is our W1, sin alpha by R is our W2, minus P by R is our B. So left hand side can be written as W transpose X plus B, and right hand side is minus 1. And what is the equation in the middle? Our line, right, which we want. That equation of that is X cos alpha plus Y sin alpha equal to P. Now you can always divide, right? You take this P in the left hand side, so it becomes X cos alpha plus Y sin alpha minus P equal to 0, and you divide by R. It becomes again cos alpha by Rx, sin alpha by Ry minus P by R equal to 0. So that is W transpose X plus B equal to 0, right? You see here, this can be written as this one. So whatever we were saying in my previous drawing here, we can adjust the coefficient of X, that weights or the direction ratios, so that equation of our line, target line, is W transpose X plus B equal to 0, and equation of the line which is in the boundary of the positive class is W transpose X plus B equal to plus 1, and boundary of the negative side, negative class, is W transpose X plus B equal to minus 1. Just we have adjusted this W such that these lines becomes like this, such a simple one. Actually here the primary objective is to make this right side as plus 1, so that we can generalize this one, right? This is one very good thing. Another one, to make this right side 1 will help us once you see how to find out this width. Now you see this width, we do not know actually what it is. We have assumed it is R. Let us see if we can represent, or if we can find this width in terms of the W, the direction ratios, whatever you call it. Let's see. Okay, I'll explain that here. Before I explain that, just to capitulate the dot product of two vectors. Okay, now forget about all those whatever we have discussed. Now suppose we have a vector A here and a vector B here. Now what is A dot B? We know A dot B is nothing but modulus of A, magnitude of A, into magnitude of B into cos theta. Theta is the angle between the two vectors. We know that, right? Now what is this actually? This is nothing but this A, magnitude of A and B cos theta. What is B? B, this is B and cos theta. B cos theta is nothing but this OP, right? You draw the perpendicular from the B vector on the A vector, then this projection, this is called the projection of B on A. So what, in another way, what we can say, dot product is nothing, dot product between A and B, between two vectors, is that magnitude of a vector and the into multiplied by projection of the other vector on the same vector, right? So A dot B is equal to OA into OP. What is OP? OP is the projection of B on A. You can do it the other way around. You can draw projection of A on B as well. You draw the perpendicular from A on OB, then you multiply B with that projection, right? So projection is clear, I guess. Now dot products provides us, this is fine calculation, but physically what it is, projection between two vectors AB is equal to magnitude of A into projection of B on A. Okay. Now suppose E, E is the unit vector in this direction. Unit vector in this direction. Okay. So what is if I want to find out what this OP is, right? Projection of B on A. I'm interested to find out what this OP is. Now you find out the unit vector in the direction of A, right? What is the unit vector of in the direction of A? You take the vector and divide by its magnitude modulus A. That would give you the unit vector in the direction of A. Now you perform dot product between E and B. E dot B will give you modulus of E, modulus of B cos theta. What is modulus of E? That is unit vector in the direction of A. So it is 1 into modulus of B cos theta, that is OP. Now if you have to find out projection of B on A, the simple way is to find out the unit vector in the direction of A and you perform dot product with B. You will get this projection. Unit vector in the direction of A and B. You perform the dot product, you will get the projection of B on A. Remember that. This is what is required to find out the margin. Okay. Now come to the next slide. Oh, that is again at the top here. Okay. Now you take, suppose we have a point here, x plus, and we have point here x minus. X plus is a point on the boundary of the positive class. Now you see, what is OC? OC is nothing but the projection of this x plus vector on this normal, right? OC is the projection of x plus vector on the normal. How to find that out? If we can find out the unit vector in the direction of normal, which is nothing but W by norm of W, right? Because in this direction, what is the vector? That is W. Now you divide W by norm of W, that is magnitude of W, you will get the unit vector in this direction. So W by norm of W dot x plus will give you OC, right? And what is OA? OA again, direct unit vector in this direction, right? W by norm of W, and you perform dot product with x minus, you will get OA. Now you subtract OA from OC. OC minus OA will give you this width, right? This 2R, and that is the margin. And that's what we have done. Okay, you see here, OC, the projection of x plus on W, which is unit vector in the direction of W dot x plus, and OA, right? That is unit vector in the direction of W dot x minus. That gives us the OC and OA. And what is the margin? That is AC. That is OC minus OA, right? OC minus OA. Now, you see that x plus is a point on which line? This line, right? So, it will satisfy W transpose x plus B equal to 1. So, W transpose x plus B, which is equal to 1, right? And x minus will satisfy this equation, which is W transpose x minus plus B equal to minus 1. Now, what is W transpose x plus from this equation? W transpose x plus will be 1 minus B. You take this B in the other side. And W transpose x minus will be minus 1 minus B. Correct? Because x plus is a point on this line, x minus is a point of this line, they will satisfy the respective equations. That's what we have done. So, AC is equal to what I have written, this one. And what is this? I just take 1 by norm of W written here, and W transpose x plus B, as we have seen, that is 1 minus B, and W transpose x minus equal to minus 1 minus B. Now, what is this equation? The 1 by norm of W dot x plus, which is equal to 1 minus B minus W dot x minus, which is minus 1 minus B. You just simplify this, B will be cancelled out, it would be 2. So AC is equal to 2 by norm of W. That is the margin. Okay, so we have adjusted W, right? or that normal vector such that equation of this line becomes W transpose X plus B equal to 0. Boundary of the positive line becomes W transpose X plus B equal to plus 1, and this line becomes W transpose X minus X plus B equal to minus 1. Such that this has given two advantages. We can generalize, can represent all the constants, right? Or this that is this these are the constants for perfect classification of all points, correct classification of all points. We can represent them in one shot, and we can find the boundary in such a simple form, right? 2 by norm of W. Frankly speaking, I personally appreciate Hapnik Chepronenkis this mathematical, what shall I say, the beauty or magic, I tell, isn't it? You see that. Simple thing, it existed, but they could able to view if we can write the equations in a just bit different form, right? It would be such an excellent so that we can handle it or manage it easily, isn't it? So that is the beauty. So sometimes, right, when maybe you are feeling very hungry, you are at home and there is not many things, right? Maybe you're in your mom's fridge, there is not many things, but she will bring out very simple things and she will cook a fantastic food for you, right? Sometimes I think all of us have experienced that. And I feel the same thing. There is not much things, but using very simple stuff, our moms can make, right? Or some now my wife, our wives, right? They can make very good food for us. So it is like that. Using simple mathematics, right? You have seen that simple x cos alpha plus y sin alpha equal to p, right? The normal form of the equations they have taken, and simple dot product, nothing else. But they have actually cooked a beautiful, fantastic food for us. Okay, like our moms, our wives, they do, frankly speaking. We do not have that much. Maybe Swarup can cook. Swarup is a good cook, I know, because he stays alone in Gangtok most of the time. Right, Swarup?
Yes.
Otherwise, only our moms,
You're
mother.
taking all public. You're making all my secrets public.
I think your some most your students they also know it. Huh? Okay, sorry about that.
Yes.
Okay, so that is the one. Now let me write down this whatever we have come up with. PC has helped us to come up with actually, not myself. Now what the problem is? Our problem was two, right? Our problem was one to find a perfect classifier, and that we have split it into two parts. First one was the classifier, all the points should be classified correctly. The second one was the margin is the maximum, right? That was the second one specifically for the SVM. So no longer earlier in artificial neural network and PLA, we didn't consider that. And SVM has considered that. That's why it is the best classifier. Okay. Now let us write down all those things mathematically. So our objective is to find the W. W is the only unknown. We are given say capital N number of training samples, right? N may be thousand, N may be millions. Does not matter. But if it is in two dimension, W, right, contains only two parameters, W1, W2. If it is in D dimension, there is D parameters, W1, W2 up to WT. And what is this? We have to maximize this margin 2 by norm of W, right? And what is this norm of W? That is square root of W1 square, W2 square up to Wn square or WD square, whatever it is, if there is D, right? In two dimension, it is square root of W1 square, W2 square. There is a magnitude of a vector, we know that. We have to maximize this. Subject, this is the maximization margin, the second objective. And the first objective was to classify the points correctly. That comes here, right? This is for the nth point, 1 point, that is yn into w transpose xn plus b has to be greater than 1, or maybe you can write greater than equal to, because some of the points will be on the boundary as well, right? So this is the one. But how many such constants we have? Capital N number of data on our N, because this is the it has to satisfy for all the data points. So I have to have capital N number of constants. I will say constant. It has to be there, right? This is the first objective we had. All the points has to be classified correctly. And this point is the maximization of the margin, the second objective we had. That boils down to this problem. And this is clearly an optimization problem. Now we are going to the operation research, right? Optimization. Don't worry. I'll I'll try to tell you what the solution is and all those things, how to solve it. Okay. So this is the problem, optimization problem, where norm of W is equal to this. And what I can write here, this one is equal to, I can write W dot W, right? You have got W1, W2, WD, W1, W2, WD. You do the dot product, right? That is W1, W1 plus W2, W2 plus WD, WD, right? So this can be written as W transpose W or W dot W. W dot W means W transpose W. W is a column vector, right? W1, W2, WD. So you take transpose, then write down the column, and then you product. You matrix multiplication or vector product, whatever you write, to the power half. Now you see, we are maximizing 2 by norm of W, right? Now we know we can always transfer this problem as minimization, because we do not like to have this set of variables in the denominator. That is sometimes is problematic for us. You see, we do not like harmonic progression. We like arithmetic progression, right? If there is a problem of harmonic progression, we always convert that to arithmetic progression, so that it is easy and it is easy to perceive. Here also we'll do. If we want to maximize something, that is the same problem as minimization of its reciprocal, right? We can do that. So instead of maximization 2 by norm of W, we can always write, we'll minimize half into norm. It is same, right? We can write it down. Again, so what I can write down that one, and then what is this norm? Norm by 2, right? We want to minimize. Now what is this norm? Norm is equal to W dot W to the power half. Again, square root. Who likes it? And since all these are positive terms, minimization of its square will ultimately minimize the square root of that, right? Since this within the square root term, this expression is all positive, right? So we can always minimize this square of it. That would in turn minimize square root of it, right? No problem. Now suppose if we have, say, square root of x square, right? Or square root of x, frankly speaking, square root of x. X is positive. If x is positive, if you want to minimize square root of x, you minimize x first, normally, without x square root. You minimize x and you perform square root, you will get the actual value. You can always do it. There is no harm. So instead of minimizing norm by 2, what we will do, we will minimize norm square by 2. Now, what is norm square? Norm square is nothing but W transpose W or W dot W. That's why the same problem becomes minimization of half. I've taken the reciprocal of it, and instead of minimizing norm, I'll minimize norm of square. Okay, this is not always possible if this would have been less than 0, right? This is, fortunately, this is positive, so we can always minimize the square. That would in turn minimize the square root. Okay, so this is what we can, this problem in turn becomes, it is a maximization, but we can minimize this. That would in turn maximize 2 by norm of W, and subject to the constants the same set. Okay, so this is the problem. Actually, how to solve it? Okay, this is the primal problem, they say, but this is not primal SBM, but primal SBM will come just maybe after a couple of steps. So we have to solve this. This is clearly not a linear programming problem, okay? Because this one, right? This is a quadratic term. This is non-linear. So this is a non-linear programming problem, we can say. And to solve the non-linear programming problem, we do not need to worry. Lagrange, right? Famous Lagrange has given one technique to solve it. Actually, this is the optimization problem. If any of you have studied, you might have seen that how to incorporate these constants within the objective function. This is the objective function. Our objective is to minimize this subject to these constants. And these are the constants. And Lagrange, what he says, that he has says that we can construct a new objective function incorporating the constants. Okay, and if you minimize that, that would in turn minimize this objective, and these constants will be satisfied. Okay, Lagrange, great. And that particular function is called Lagrangian function. Okay, and for this problem, Lagrangian is very simple. I will explain it, listen it carefully, you will not be doubtful. Because in the optimization, there can be, this can be maximization, unlike here it is minimization of the objective, but it can be maximization of the objective. These constants can be greater than equal to, these constants could be less than equal to, right? So there may be confusion. Now let me tell you what to do. If this is minimization problem, the problem will be minimization, and the Lagrangian will be a function of the same parameter. What are the parameters here? We have unknown parameters at W, and there is a scalar B, right? We do not know what they are, W and B. W, how many W's are there? There are how many components? W1, W2 up to WD. Okay, so two set of parameter. I'll introduce another. I have to introduce by actually Lagrange has suggested alpha 1, alpha 2, many. Well, I'll explain that. First, you just write down blindly what the objective function. Does not matter whether it is maximization or minimization. You write down that one. Then there will be some plus. As I said, right? You have to incorporate the constants. You take one constant. Here, all the type of constant is same. So I'll take one constant, right? Nth constant, that is this one. You write down that. What I have done here, I have written here 1 minus this. Since it is minimization, you have to convert these as a less than equal to constants. To make it less than equal to, you take this whole thing in the left hand side. It would be 1 minus this one will be less than and equal to 0. If it would have been maximum, we would have been done it greater than equal to. In that case, we have to take this one in the left hand side. So it is a minimization problem. You take this whole thing in the left hand side. It is 1 minus yn into w transpose xn plus b, right? That is the constant for the nth data point. And then you multiply that by a constant alpha n. Okay, I'll tell about alpha n. Another parameter we have to introduce, alpha n, for the nth constant. We have done it. Now, how many n's are there? There are capital N. It may be 1,000, it may be 1 million, depending on the number of training samples you have with you. So for everything, you have to write 1. So there will be capital N number of terms like this, and capital N number of new parameters we have to introduce. So I have written here n equal to 1 to capital N, alpha n into this one, where alpha n has to be greater than equal to 0 and are called Lagrange multipliers. Okay, you see the problem. Our objective was to find W and B. If it is in say 10-dimensional data we had, so our parameters was only 10 plus 1. In 2 dimension if it is, then there will be W1, W2 and B3 parameters we had. Now if we have say 1000 data points in 2 dimension, so far we were trying to find out the values for 3 parameters, but now after this Lagrangian, how many parameters we got? The alpha n's are unknown to us. 3, because W1, W2 and B, together with this 1000 new, right, headaches, I will say. Alpha 1, alpha 2 up to alpha 1000, those many parameters, right? So it's like, what shall I say, that you wanted to have a simple solution, alpha n, y n, x n, and last term is alpha n, y n, b with a minus, and that is also no w present, that would be 0. So if I differentiate this Lagrangian function with respect to w, it becomes this one. This gives us w equal to summation alpha n yn xn. Okay, here we get. Now if differentiate this with respect to b is another parameter, right? This part is 0, this part is 0, alpha n yn w transpose xn is also 0. There is only one b. What is that? Alpha n yn b with a minus, right? So it is alpha n yn with a b differentiated with respect to b, it becomes minus alpha n yn equal to 0, right? So we got w equal to this and summation alpha n yn equal to 0, these two. Okay? Now, what we do, we replace this w in this equation. Let's see what happens. If we can get rid of some of the parameters before we differentiate the whole thing with respect to alpha, we can replace that one. Okay? We just try to put w here. Don't worry. You see here, w, right? It is a very big expression though, it looks like, but it is not easy. You can write yourself, it will be very easy. There is one w transpose and one w. So, for w transpose, there will be one set of alpha n yn xn transpose, right? You take a transpose of this, there will be a summation alpha n yn xn transpose, right? And instead of putting the index as n, I put here m, that is alpha m ym xm transpose. This is for w transpose. There is w, right? And w can be replaced as this alpha n yn xn. I have done it, alpha n yn xn, right? And this half is always there, half is there, and there are two summations. One is on this m, another one is on this n. No problem, right? We can replace this w using this one. One index is for alpha w transpose, another index n is for w. Now come this. There is one simple, right? You just split it. This is 1 into alpha n, that is summation alpha n. Now go to the next one. Minus alpha n yn w transpose xn. Xn is the right side. So that w transpose again can be replaced as summation alpha m ym xm transpose, right? Like we have done here. And so it becomes alpha m ym xm transpose. And for the other one, whatever we have got existing alpha n yn xn, I have written here. This and this term are same, right? Here it is half, here it is minus. No problem. Come to the next. Alpha n minus yn into b. I have written here. Okay? So we have split this, we have replaced w, and we got this one. You see, we would have been very happy that if there was no half here or there was half here, right? But unfortunately, it is not. We cannot get rid of this. So if I subtract and simplify this, I can write down this plus alpha n here. Here it would be minus half of this double summation, this one. And what is this? This is 0, right? Summation alpha n yn equal to 0. So we got this one. And we have to minimize it. And note that all these alpha n's are greater than or equal to 0. And this is called the primal SVM problem. Okay, primal problem for solving SVM. Okay, note that our objective is to find W and B, right? But what we got rid of all the W's and B's here. No W and B here. That is surprising, isn't it? But don't worry. If we can find out, if we can solve this equation, right, this minimization problem for alpha, if we can find all the alphas here that minimizes this expression, we can find out W and B. That is very easy. You find out all the alphas, and we know what is W here, right? You put here, we know all the yn and all the xn's, and you find out all the alpha n's, and you multiply these and sum them up. You will get W. Don't worry. And you take this W and put in one of the equations, right? W transpose x plus b equal to 0. You take one of the point, right? On the boundary, right? You take one of the boundary point and put on those equations that W transpose x plus b equal to plus 1, right? In the plus, and you will get b as well. Okay? So don't worry. So we have to find out W. Now, to solve this one, we will be using some theorem of operation research called KKT theorem. Okay, KKT theorem. Instead of solving this directly, we can solve the dual, because solution of the dual problem provides us the solution of the primal. I'm not going to the dual and all those things. Fortunately, actually, I studied operation research in detail. That's why it was very easy for me to appreciate. But here, whatever I am telling you, you accept it, and later you can learn of your own in detail. Okay, so this is the equation. We'll be writing the dual of this, and we'll solve the dual problem to obtain these alpha values, because we have to alpha. How many alphas are there? 1, 2, up to capital N number of data points. And what KKT theorem, KKT, the full name is Karus. This first K stands for Karus, one famous mathematician, Karush. This K stands for Kuhn, Kuhn, German mathematician. This T also stands for another German mathematician called Tucker, Tucker. Karus Kuhn Tucker theorem. This Karus may be Hungarian, most probably. Anyway, actually, sometime in 1960s and all those stuff, this particular theorem that if we can solve the dual, you can find the solution for the primal as well, or vice versa. That particular theorem was proved or popular by this Kuntakar. They have proved. Kuntakar is very famous in operation research. They have got many theorems. Okay. Now Kuntakar has come up with this theorem. But later, people found Karus in 1930s has already proved this theorem. Okay, to give respect to Karus or recognition to Karus, they named this theorem as Karus-Kuntakar's theorem. Okay, that's very nice. Like our say, you know that nowadays this beta, right, this radio wave was discovered by Marconi. It was famous. He was recognized for that. But now IEEE has recognized J.C. Bose, Jagadish Chandra Bose has recognized or invented radio wave in the past. That's why they have now recognized that this Bose has invented radio wave first. Anyway, so Karus-Kuntakar's theorem proved that if you can write the dual of this, and you can do it. Dual is very simple. So obviously dual will be the opposite to this. If it is minimization, it would be maximization, and dual I have given the name d of alpha. This is only the function of alpha now. Forget about WB. So alpha will be same as this, and constants are alpha n is greater than equal to 0 for the primal. But there is another set of constants was added right here. There is alpha n yn equal to 0. So this is also another set of constants for the dual. So this is the dual problem for the SVM, Lagrangian. This is clearly a quadratic equation of alpha, right? There are linear terms, alpha 1, alpha 2, alpha 3, up to alpha n, and there are all the quadratic terms, alpha 1, alpha 1, alpha 1, alpha 1, alpha 2, alpha 1, alpha 3, alpha 2, alpha 1, alpha 2, alpha 2, like that, right? So this is a quadratic term. These are the coefficients for the quadratic term. We know, right? If we have all the points, we can always calculate the dot product of them and multiply by their levels, we'll get these things. These are the quadratic, and together with this minus half, right? They are the coefficients, and coefficients of linear terms are 1. And these are the constants we have to fit. Now forget about all the theorem. Now let us have one QP solver, one black box like this. Now you might have written already some program, right? Say, Sarup sir normally whenever he teaches say, languages and all, you write a program in C or in Python to solve quadratic equations, right? Whenever we write the program, we do not fit the equation, right? What we fit the coefficient of x square, coefficient of x, and the constant term, and then we solve it. So here also, we have a QP solver here. You feed the coefficients of the linear terms, coefficients of the quadratic terms, and the constants, and this QP solver will give you the alphas. Okay? Now just to tell you, coefficient of linear terms are very simple. Now what are the coefficients of the quadratic term? Coefficients of quadratic term, there is a minus half multiplied by this term, right? This expression. And what they are, if I can write down here, right, for each everything, there will be total n squared term. n equal to 1 to n, n equal to 1 to n, right? It will look like this, a matrix. If you write alpha 1, alpha 2, alpha n, this side also alpha 1, alpha 2, alpha n, you see that, as I was trying to say, alpha 1, alpha 1, y1, y1, x1 transpose x1. So what is the coefficient of alpha 1, alpha 1? That is y1, y1, x1 transpose x1, right? What is the coefficient of alpha 1, alpha 2? You just put n equal to 1, n equal to 2, you will get, right? y1, y2, x1 transpose x2. What is the coefficient of y2, alpha 2, alpha 1? That is y2, y1, x2 transpose x1, right? This is the one. And since it is a dot product, right? X transpose x1 or x1 transpose x2, they are same. So this matrix will come up, coefficients, right? We can generate this matrix to obtain the coefficients of quadratic terms with a minus half, right? And you feed to this solver with this constant term. And note that how many coefficients should be there? N cross n. So if you have 1,000 data points, it would be 1,000 by 1,000. If you have a million data points, you will have million by million. It is a huge. But anyway, machine will do it and we can compute this thing easily. Now, this is very nice. What I have written here, most of the alphas will be 0. Once you get the result, after feeding these coefficients and these constants, you will get a set of alphas, right? How many alpha we have? Capital N number of alphas, right? And you will see that most of the alphas are 0. Like if you have, say, 1,000 data points, there will be 1,000 alphas. And for your surprise, maybe 995 will be 0. Maybe 5 will be non-zero. Okay? Now you will be surprised, right? Is there something wrong? I failed all those things. There are 1,000 alphas. Why so many alphas are 0? Only few non-zero values are there. Because alpha, all the alphas are greater than equal to 0. Okay? Actually, the alphas corresponding to the points, okay, they are these. I'll tell you. Come to this. Here, you might be having lot of minus points here, right? You might be having lot of plus points here. You see, on the boundary, you have got only 1 point here in the positive side, and in the negative side, you have 2 points on the boundary. You may be having, say, 500 points, right? Including these 2 in the negative side and 500 in the plus. But how many are there on the boundaries? There are only 3, right? Only 3. 1 in the positive and 2 in the negative side. So these 2 plus this one, corresponding alphas will be non-zero. All the alphas corresponding to all the interior point they call. That means interior means inside the negative class, inside the positive class, corresponding alphas will be 0. Okay? And that is why you will get only 3 non-zero alphas in this case, and 997 points, if we have 1,000 points here, alphas will be 0. And it is not only, say, practically whatever solution we got, that KKT, that theorem also confirms that. What KKT says, I'll come back here. I think I have written down here. Oh, yes. What KKT says that at the optimum point, when we get the optimum alpha, we know that, and that for all this this was a constant, right? This was a constant, and we have multiplied alpha and we have added to the Lagrangian. This product, alpha n into this, will be 0 for the optimum alphas. So if we can solve for optimum alpha, this will be equal to 0 at optimum point. Okay, at optimization, this will be 0. Now you see, for the boundary points, if xn is a boundary point on the either on the positive boundary or in the negative boundary, they will satisfy this equation. This part will be equal to 0, right? Then alpha n may not be non-zero. It is not necessarily 0. But if the point is not on the boundary, what should be the value of this expression? If it is not in the boundary, this one will be greater than 1, strictly greater than 1, beyond the boundary, right? So So yn w transpose xn plus b will be greater than 1. So 1 minus this will be strictly less than 0. So this expression is strictly less than 0 for the interior points if it is not on the boundary. Then alpha n has to be 0. Okay, that's why for all the non-boundary points, alpha n are 0. Okay, and those alpha n's, okay, see here it is alpha, somewhere here on the boundaries, those alpha n's are supporting this avenue, right? They are supporting this avenue. That's why they are called the support vectors. These points means vectors. This is one point, this is another point, this is another point, right? So these 3 points, and points are nothing but vector to us, right? And that they are supporting this boundary. That's why they are called the support vectors. Okay, that's why the name came support vector machines. This technique machine finds out the support vectors and provide this line. Now, once you can find out the non-zero alphas and the corresponding points or the vectors, okay, then it is very easy. Now see, what is our W? Our W was this, right? This one. You see, most of the alphas, there are say 1000 alphas, then this summation will become very easy. Only three alphas are non-zero, so it will be sum of only 3 terms, right? Maybe say for simplification, or we can assume that maybe x1, x2, x3 are the 3 points. So it would be alpha 1, y1, x1, alpha 2, y2, x2, alpha 3, y3, x3. And perform that, you will get W. Okay, so you get a W. Now, you see, you got x1 as a support vector. So x1 will satisfy what? It would satisfy this equation, right? Sorry, what is that? It will satisfy W transpose x plus b equal to +1 if x1 is in the positive boundary. If it is the negative boundary, it would be satisfying this equation, right? So you can put x1 in this, or maybe x2, x3, they are on this line. So you can put any one of these, x1 on this, x2 on this, or x3 on this. You will be able to find out b as well. Okay, so we got W. We can calculate B in 3 different ways, because for every support vector you will get a B, and all the B's has to be same. This is mathematics, right? Concrete mathematics, no approximation, nothing. So you will get B as well by using one support vector on this line. So we got W, we got B. So we got this equation, right? W transpose x plus B equal to 0, and W transpose x plus B. Now, whenever you got an unknown point x star, what you do? You put here. Find out the value of W transpose x star plus B. If it is greater than 0, we can classify x star as in the positive class. Otherwise, it is in the negative class. Okay? So, this is the support vector machine for linearly separable data for 2 classes. Okay? Now,
can you please repeat once again? I could not able to follow. I mean, how to classify based on those.
Okay. You got how to find, you know that now what I said, that we have already found out the values of the alphas, right? Alphas are the nothing but the Lagrange multipliers, right? Now, what we have seen that most of the alphas are 0 except a few, right? And those 3 alphas corresponds to the points lying on the boundaries, okay, and they are the support vector. Using those support vectors, using the line W equal to summation alpha n y n x n, we can find out the value of W, correct? Up to W it is okay for you, I guess. Now you take a support vector. Suppose this is a support vector and this is x1. So x1 will lie on this point, this line, right? So x1 will satisfy this equation. So W transpose x1 plus b equal to 1. W we have already calculated. X1 we know. We can always find out the value of b. Correct? So we can find the value of b. Now we got W, we got b. So we know what this equation is. Now if you have to find out the class of an unknown point x star, you use this. You calculate the value of W transpose x star plus B, right? Then if it is greater than 0, x star will be in the plus side. If it is less than 0, it would be in the minus side. Correct?
Yes,
Correct?
yes.
Okay.
Yeah, yeah.
Okay. So that's what is actually our linearly separable data. Now, what happens if the data is not linearly separable? Actually, there are two concepts. I'll come back. Just hold on. I want to stop sharing that and okay, stop. I'll come back to my Povitro's presentation or this presentation. I have modified a little bit and
And
described.
Dinamanta, one more thing, as a computer science people, I mean, we prefer more the algorithmic view. Can you show the algorithmic of that? Algorithmic view.
I understand. You see, what you have to do is that algorithm is very simple, right? You have to construct that particular. Just hold on. Let me come back to this, and I'll explain that. Very nice. This is the mathematical part, right? Okay. Okay. What I can say is that you find out this matrix, okay, which is nothing but y1 x1 transpose x1 or dot product of x1 x1. So this matrix you calculate first, and then you use one QP solver to feed the coefficient of alpha square and coefficient of alpha and these constants. There are a lot of QP solvers are available now. Okay, in different tools. Actually, in this presentation, you have got the references as well. You can see that later. So you can use QP solver to solve for W alphas. Now, once you get the alpha, then everything is known. Sorry, alphas. Then you can find out the W also, right? Summation alpha and y and xn. Xn is a vector of magnitude d, and that would give you the W. You can find out W, and then you use one of the equations, right? The W transpose xn plus b equal to 1 with a multiplied by yn. You just put one support vector on that and calculate the value of b. I think anyone can do that. You just see that, and everybody can just think of an algorithm, calculate the value of b. And our objective is to find the value of W and B. Once you get the W and B, then after that, the writing program is not an issue, right? What do you say, Sarup? Anyway, that you can give a search, and or you can think of it, and you will be able to find it out. That is not an issue. Okay, and now after studying all those things, I guess that I do not need to explain that in every step of the what shall I say? You calculate the coefficients of those alpha square from that expression, and then you use one QP solver. Tools are available. You can feed it, and then find out the value of alphas. Use the non-zero alphas to calculate the value of W, and from this you can find the value of B, and then you can classify the points correctly. Okay? And there are some examples in the presentation. You can have a look and see quadratic programming. Different references are there. You can look at it later. Okay. Now already 12:30. Let me go very fast about this non-linearly separable problem. Actually, this one is they call the soft margin. You can reduce the margin. For that, you just read it yourself. I am not going to do that. I'll just explain a little bit of this kernel optimization. Tomorrow, if possible, before I explain the deep neural network, maybe I'll come and explain this particular soft margin part. This is very, very popular and very important one. Just today, I'll try to explain the what shall I say? the kernel trick, huh? Or I'll do the other way around. Maybe I'll explain the soft margin today, and tomorrow I'll explain. Let's see how far we can go. Huh? Okay, I think better to go through this one. Soft margin concept is that there is some compromisation here. Okay, suppose you have a data set something like this. Now you see, if I have to find the boundary here, what should be the margin? Then you can see there is a little space here, right? I can draw a boundary here for the circle, and for the square rectangle I have drawn here, right? So there will be very little margin. Instead, if we can allow some of the misclassification, only one misclassification here, and this one also allowed, but if I take two misclassification in some sense, but ultimately this is not a misclassification, I can draw the boundary here, I can draw the boundary here. There are a couple of one misclassification, but that is giving us very good flexibility, having the higher margin. You understand that, right? It's like, suppose you are walking across a football field. Maybe in the center place, there is some mud. It was raining and there is some mud, right? And if the mud is quite, or maybe if you can see that only couple of steps, if you can be careful, then you do not need to take a longer route to reach the other side. You go ahead with that, right? It's better. Okay, it may make my shoe bit dirty, but does not matter. I'll just walk because it will save a lot of time for you. You compromise on it. Another way you can say that if you travel by say air, right? Sometimes you will see that pilots has some options to go around to avoid some cyclone or something. But sometimes if they say the cyclone is okay, it may just shake the plane little bit, aircraft little bit, let the passengers be afraid, but does not matter. It is safe to fly through this cyclone. They will just take the route and they will fly through the cyclone for 5 minutes. If they had to take a detour, maybe they had to travel say 10 minutes or 15 minutes more, right? That would consume more fuel and all those things. So it is like that. So you compromise, you accept small error, but it would give you very good flexibility of a higher margin. You can save more. That is the concept here. Okay. Another way that you draw something like this, curved line. I'll come to that in the next one. But here we'll follow the same linearly separable data with some error accepted. Okay, that's what. We allowed error xi I in classification. It is based on the output of the discriminant function W transpose X plus B. Xi I approximates the number of misclassified samples. How much you are allowing. Okay, xi I. Now xi I you reduce, you are you are not allowing much. But you increase the xi I, that means you are much more flexible. Okay, that's what it does. Now, this is the one, right? This line is W transpose X plus B equal to 1, and this line is W transpose X plus B equal to minus 1. This is 1. But for this point, what we can write here, the W transpose X plus B, for these points, what it would be? It would be not only greater than 1, but it would be greater than 1 minus xi I, right? That I'll show here. That is 1 minus xi I. Earlier, we were strict, right? There is no flexibility. Strict, that is 1. And for the negative side, it is 1. But what you are saying now, it is 1 here, and you are allowing further, right? Minus 1 plus xi I, isn't it? That is minus 1 plus xi I. Another xi I also you can allow, right? It can be, but it would be okay. And for this one, it would be 1 minus xi I, right? This side. So instead of writing strictly 1, you are allowing, right, some variable. Now, depending on the xi I, you are making yourself that much flexible. Say, if you have, say, put only 2 steps, or maybe you have to fly through the cyclone for maybe 5 minutes, you will go. But if the cyclone is maybe 10, 15 minutes, passengers will be afraid, and pilot, it is better to take it, right? So that how long you have to travel through the cyclone, right? If it is 5 minutes, maybe 7 minutes is okay, but more than 7 minutes is not allowed. Pilot always decide to take a detour. So it's like that, xi I, right? They are called slacks, and all these xi i's are greater than zero. These xi i's are called the slack variables in optimization, in operation research. And note that xi I equal to zero if there is no error for xi. If you do not allow, so xi I equal to zero, right? That's what we have studied. That is what, okay, soft margin, and that is the hard margin we call. Xi I is an upper bound of the number of errors, right? It is clear. You increase the xi I, you allow more number of errors. You reduce the xi I, make it zero, no error. Now, in this case, earlier one, what we had to minimize this part, right? Now, we do not want this xi I should be very high. So we want to minimize summation xi I as well. How many are there? N number of there. But there is a constant term we add here, C, right? This is somehow, it helps us to adjust which one will get more priority. Will you give the summation xi I as more priority? Then you increase the value of C. That means you just do not try to allow, do not allow much. Okay, then you increase C. You increase C means xi has to be small, right? You do not want to be very, very flexible. Now, you reduce the value of C means you are quite flexible. You understand? So, this is somehow controlling parameter capital C. So, this is the trade-off parameter. Okay? You increase the value of C means you do not want to allow many errors. You decrease the C, you are ready to allow. You are very, very flexible. So that's how we do it. And in operation research, this is quite a common practice. We do that. Okay. And subject to the constants, this one. So we can multiply yi this one and yi this one. It will become, instead of one earlier, what we got here is 1 minus xi I. But unfortunately, we got another set of constants here, xi I. Don't worry. Okay. Lagrange is there, so we have got the solution as well. Now, what would be the Lagrangian? This is the objective function we have written, and this is the parameters we had, sorry, constants we had with alpha I, and there was another constant, right? Xi I greater than equal to 0. As I said, you convert that to less than equal to, so xi I has to be minus xi I, right? Less than equal to 0, and there will be another set of Lagrange multipliers, mu I, right? You are wondering. Here we got n number of parameters, you got another n number of parameters, but does not matter again, I'm telling you. Now, all these alphas and mu's will be greater than equal to 0. Now to solve it, same thing, we differentiate this L with respect to W, and you will get W equal to a summation alpha I, yi, xi, right? You can see that. Respect to W here, and only one set of W here, and you will get it. Now multiply this with respect to B, it is same, right? B is there already involved, where alpha I, yi, and B. So it is same as this one, right? Another set of parameters xi I we got, and differentiate this with respect to xi I. Here you got C here, and xi I is there here. There is minus alpha I, and xi I is here minus mu I. So you got another one, right? 0. So these three equations, this W you put here and use this, it would be a very fun. Okay, you replace that, and we got this one. Just earlier case, whatever we got. And but good thing is that you see that for the xi I, you got C here. For the xi I, you got minus alpha I, and for this xi I, you got mu I. So it would be summation C minus alpha I mu I into xi I. And we know from here, right? They are 0. So everything will be cancelled out. You just see the mathematics, everything will be cancelled out, and you will get the same alpha, same primal problem what you got for simple hard margin, for soft margin also same. But here, one constant is different, that is alpha I, right? What we have got here, C equal to this, right? Alpha I, this one. Now, if you get this mu j, right? This is positive. So alpha j cannot exceed C, because C is equal to alpha j mu j. This mu j is again positive. So alpha j is positive, but it cannot exceed this limit C, right? This compromise parameter C. So only difference here is this one. Earlier case, what we had, there is alpha I is equal greater than equal to 0, right? That was the only constant for the hard margin case, but the for soft margin case, alpha I has to be less than or equal to the C value, the compromise parameter. Okay. Now constants derived from C equal to this and mu alpha for positive. You can go through this one. Okay, and alpha I yi equal to 0, same as this, and you can solve it using that. Now, if alpha T1, T2, T3 are the support vectors, you will get W, and it is the, you use the QP solver and you will get the same thing. Okay, that's how this one comes out. The algorithm try to keep Xi null, maximizing the margin. The algorithm does not minimize the number of error. Instead, it minimizes sum of distances from the hyperplane, if C equal to 0 or something like that. When C increases, the number of errors tend to lower. At the limit of C tending to infinity, the solution tend to that given by the hard margin formulation. Obviously, right? You want C equal to infinity, then Xi I has to be 0, right? Otherwise, this will dominate. Okay, so then we go back to the hard margin. If C is very 0 or very small, does not matter what about the Xi I value, you are very, very flexible. Soft margin case. Soft margin is more robust. That's what they say. Maybe you accept couple of errors, but it is very nice. Otherwise, you would have been got very small one. So soft margin and hard margin, there is some differences. Anyway, depending on the value, you can adjust the value of C and you can go for soft or hard. Okay. Now, this is another concept. Only 12:30, and I'm also getting tired. This is anyway. I'll try to explain that. Yesterday,
I think that it may able to that soft boundary can able to handle noise also.
you are right. You are. If the noise is there, and if you have got say noise and an overfitting problem, right, you can avoid it.
And that the boundary can be maximized also. What I can
Yes,
say.
yes, yes. You are right. Hey, Swaroop,
Yeah.
can you do one thing?
Yeah.
Is it because this kernel concept, right? Non-linear separation. That is another beautiful concept, and that needs actually fresh mind to understand, frankly speaking, and how we use, how we can take the point into the higher dimension, how this dot product will help us. Can we take say tomorrow in the morning half an hour? Okay. If you
Okay.
mind, if you don't, if all of you do not mind, we can start bit early. So
Okay.
maybe 10:30 or 10:45.
10:30 you can 10:30 you can start.
10:30 will start
Ah.
because I am also getting tired. You know that in wave, in online lecture, it is very difficult to talk, right? Alone.
Right. Right.
Maybe I'm shouting unnecessarily just to convince you guys. If we could see you in front, your body language, it would have been easy for me, right? So it is really tiresome to talk online.
Long.
So I think that is okay, right? If we can talk tomorrow, we can start at 10:30. Please bear with me so that
All the participants, is it okay for you?
Yes, sir, it's okay.
okay. Then
Yes, sir, it's okay.
okay,
So
thank you
almost
very much. Thank you very much. Now, if you have any questions so far, whatever we have discussed, please ask me. Otherwise, you can go through my notes as well as the presentation. You prepare the questions. You ask me tomorrow. I would love to clarify them. Because what I feel that this is a fantastic application of simple mathematics, how one can develop such a powerful tool using simple things. Okay? And you please go through that. If you have any doubt, again, you can ask tomorrow or maybe later also you can contact me. I will be very happy. Okay? If you have now any question, please ask me. Otherwise, we will stop. Dibba, you want to say something?
No, sir.
Okay.
So if no one having, I have again, I may be
Yeah.
wrong. I may be wrong. I try to draw some intuitive idea from overall
Yeah.
of the overall PA. So here, I may be wrong. So the WTX plus B equals to plus 1 and WTX plus B equals to minus 1. These are the two lines. Are you using to draw the WTX plus B equal to 0? Are
Yes.
you? Okay.
No, you are right.
Okay.
W transpose X plus B equal to 1 and W transpose X plus B equal to minus 1. Okay. Those are
Okay.
the two lines we
Right.
are drawing. We are
Okay.
actually finding out fast
Right. Hmm.
so that we can get a line in between them
In
as a
between.
boundary. You are
Right.
right. You are right.
So then based on that equal to 0 line only, we are doing all the classifications.
Yes, because once we get the W transpose X plus B, W and B, we can always get W transpose X plus B equal to 0, right? That is our ultimate objective. To
Right.
find W transpose X plus B equal to 0, we are finding W transpose X plus B equal to 1 as well as minus 1. Yes.
And in terms of that non-linear one, so introduction of the error term is okay, but cannot we think of a multiple such lines, straight lines or some boundaries?
Yes,
Can we?
we can find out, we'll try to find out actually curve line, right? That's
Right.
what we look for. But
Mm-hmm.
in SVM, instead of finding the curve line, what we will try to do, we'll take the points in a higher dimensional space and we'll make the points linearly separable and we'll be using the same one. That Covers theorem, right? I was trying to
Yes,
emphasize
yes,
that Covers theorem tells that you can take the points in higher dimension which becomes linearly separable. So if we can take and if there is any mechanism to utilize that, okay, and VC, Vapnik and Chebronenkis has used that concept, okay, marvelously, I can say, marvelous concept of that is a kernel fit they call, okay, and simple dot product they will be using and kernel function, right, to find out the dot product. That's why I'm telling you that one conceptually it is bit, uh, yeah, it is very nice, but it would be easy for us to understand that in a fresh mind. That's why I'll try to explain tomorrow morning at 10:30.
So one more thing, like if I think it in another way, like basically we are trying to draw a minimum bounding rectangle.
Minimum?
Bounding rectangle. We into that space, the between the two different classes. Can we think an alternative, like to draw a minimum bounding rectangle that actually pass through the any points from both the classes?
I didn't get that actually.
No, there is
Maximum.
some
You want to find out the maximum boundary, right, between two classes?
box between the rectangle between them. So
Yes.
instead of going through that, I mean, this is a very fantastic one because once we have mathematical formulation and the minimum number of terms, computationally also it is going to take less time. But the other way, can we think of like because the overall the idea is to draw a, I mean the
Yes.
rectangle, the drawing a rectangle between the two class, taking the maximum the boundaries of that box in the two different classes, the boundaries of the two different
Okay.
classes.
Yeah, boundary. Yes.
Yeah. So that minimum boundary rectangle can we draw and then try to find out the middle line from there.
I understand what you are saying. Actually, ultimate goal is whatever you are saying. But to
Yeah.
achieve that goal, if we do something else, okay, you see
Yeah.
that maybe if someone is hungry, our first objective is to provide some good food to that person, food to that person. Now, first thing is if someone is very hungry, does not matter whatever food that person gets, he eats. Now, together with food, if the food is good, that is better, right?
Right.
Now,
Right.
food can be prepared in different ways. Now, but it doesn't matter, right? If it is a food that solves our hunger, right? That satisfies our hunger, that is okay with us. So, whatever you are saying, that is the ultimate objective. Now, to satisfy that objective, we are taking a different path.
Different way solution.
Yes,
Right.
that's actually ultimately, if you go through that, in that higher dimension, we are trying to find out the curve line, whatever you are saying. In the existing input space, we'll be trying to draw the curved line, but in the virtual space, we'll be trying a line. That line represents the curved line in your input space. Okay, in the feature space, it is a straight line, but in the input space, it is a curved line. Okay, now if you can replicate that, yeah, if you can remap that in the input space, it will be a curved line or maybe a circle or maybe a rectangle, whatever it is. You are right. The same thing. Yeah,
Thank you. So, is there anyone having any questions? Then otherwise we will wind up.
yeah, Dinesh. Yeah, actually, tomorrow we'll be discussing about RBF kernel. RBF kernel will help us to take the points in the infinite dimension and calculate the dot product of two vectors. Okay, and that is the best kernel people uses. We'll be discussing tomorrow, Binan. Don't worry. That is a kernel. There are several other kernels, right? That is the ultimate. RBF kernel, that is e to the power minus gamma x minus x bar, x minus x dash. Okay, so that is the ultimate kernel. Okay, the best. You can use RBF and change the value of gamma. There is one parameter in that kernel, and it will solve. It will be able to help you to solve any nonlinear problem. But that is the most or the best. Okay, the kernel. Will yes, yes, yes. And there are some simple kernels as well. I'll discuss that tomorrow, so that would help you to appreciate or perceive how can we take the points in infinite and all those things people say, how it works, how RBF kernel will help us to classify the data or take the points in higher dimension. Thank you very much for this. We'll explain, we'll try to learn the basic simple kernels so that you can view it, and then we'll go for this type of very powerful, very effective kernels like RBF kernel.
Sir,
Yes, yes.
sir, you taught about two-class classification. So, in case of multi-class classification, then can we think like there are more decision boundaries? That is, if there are going to be 5 classes, then there will be 4 decision boundaries. So, can we think like that?
Okay. What I suggest you just do a search in Google for multi-class problem. What we do, we can always convert those multi-class problem into binary class problem. Okay, that means one versus many or one versus rest. You understand? You take one class, classify the label them as +1, you take all other points as -1. So you can separate this particular data set belonging to that one class. You understand? Then you take the other one. So slowly you can always convert or consider the multi-class problem as a set of binary classification. You understand? So please, one versus rest, one versus many. You give a search in this one, then it will just take 1 minute for you to understand. Doesn't matter if you have said number of classes. Okay. Anyone else?
I think no questions till now. So let us wind up today. We'll start tomorrow at 10:30.
Please. Thank you very much.
Thank you.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.